Filters take away light. The graph on the left shows the spectral distribution of a light source. So for this particular light source, it gives off light in the visible range, but it gives off more electromagnetic radiation in the 700 nanometer range compared to in the 400 nanometer range. The middle graph shows you the filter characteristics. So this is showing you what range of wavelengths are actually able to get through the filter. So on the x-axis, again, we have wavelength, and the wavelength section that's being shown here is 400 to 700 nanometers. On the y-axis, we have relative transmission. So by relative transmission, this term is generally expressed as a percent. So a filter, if the curve is low down here, the filter allows very little of this range of wavelengths to pass through it. Then there's a section of wavelengths that get through the filter, and then the filter starts to block more light. And so what we have here is a light filter system. So we're going to take this light over here, pass it through the filter, and then we're going to express the characteristics of the light that comes out of the filter. So again, because the filter allowed some wavelengths through, the relative energy of the light coming out of the filter is going to be different compared to the light going into the filter. So the shape of the relative energy curve will be very similar to the shape of the filter. Again, we also have a reduction in the overall amount of light that is coming out of the filter because filters take away light. There are a number of different types of filters, such as the ones listed here. We're going to go over these in class, but we'll talk about a few characteristics in this next set of slides. If we describe filters by the range of wavelengths that they allow through, we can categorize filters in several ways. For example, if a low-pass filter is being used, that low-pass filter will allow short wavelengths to pass through, but then there's a certain wavelength that we call the cutoff wavelength, and for wavelengths higher than that, the filter does not allow those wavelengths through. So we say the filter blocks wavelengths higher than the cutoff wavelength of the radiant energy. We can also have a high pass filter. So this is a type of filter that allows the longer wavelengths through, but if the wavelength gets to a certain number, then any wavelengths shorter than that wavelength the filter does not allow through. We can have something called a band pass filter, which allows a region of wavelengths through, but for wavelengths that are longer than that or shorter than that, those wavelengths do not get through the filter. And we can also have a band stop filter. So there's a range of wavelengths that the filter blocks, but for wavelengths shorter than that and for wavelengths longer than that, the filter allows that light to get through. The four filters whose transmission characteristics are shown here over on the right, we call these broadband filters because the range of electromagnetic radiation that they allow through is rather wide. There are also some special filters that may only allow a few nanometers or even 1 nanometer of wavelength of light through that filter, and everything else gets blocked, and this is called a narrowband filter. Filters can be colored or they can be neutral in color. A neutral filter is a gray filter, but the color filter is the color of the light that's coming through or being transmitted by the filter. So all other wavelengths are blocked. So if you're sitting there holding a filter in your hand and you say, "Oh, this filter looks red to me," the reason it looks red is because red wavelengths are passing through the filter and are able to stimulate your eyes. Colored filters often are broadband, not narrowband, so there's a range of wavelengths that pass through the filter, but those wavelengths kind of center near the wavelength that is the color that the filter looks to you. Here, just for reference sake, but we do want you to eventually learn that red is down around 600 to 650, Blue and violet are the short wavelengths, and of course yellow and green are in that 520 to 570 range. So you should be aware of these ranges of wavelengths even if you don't memorize the specific colors that these wavelengths appear to people with normal color vision. Here's a concept check problem. Let's take a look at this and see if we can figure this out. Describe the color appearance to somebody who has normal color vision of the filter whose transmission curve is shown below. So let's take a look at the X and Y axes. Again, X axis is wavelength in nanometers. Y axis is the percent of incident light that the filter will transmit or allow to go through it. So we remember that the visible spectrum is between 400 and about 700. So this filter is actually blocking light until you get to about here, and then it suddenly allows a lot of the light through, and then the curve drops down again and starts blocking off the light over on this end. So because we're allowing a lot of that 600 nanometer light through, if you were to hold this filter in your hand, it would look red to you. There is a clinical condition called a rod monochromat. We're going to talk about this in lecture, but if you can reduce some of the light that is entering a person's eyes when the person is a rod monochromat, you can actually make them more comfortable, and we can do that by using this type of filter. The red light that does come through the filter actually allows them to use the photoreceptors that they actually have that are functioning in their eyes. Here's another concept check. We have the transmission curve of two different lenses, and when we physically look at the lens in our hand, both of these lenses look clear. But when we look at the curves, we can see that they are somewhat different. So based on what you know about the electromagnetic spectrum, how are these lenses different, even though physically they both look clear to you? On the x-axis we have wavelength, and again on the y-axis we have transmission. So for the lens that is represented by the blue transmission curve, when we're talking about ultraviolet light, so 200 to almost 400, not much of that light gets through. And then right around 350 nanometers, all of a sudden the light starts to get through the lens. The other lens, which is represented by the yellow dashed curve, actually starts to allow the ultraviolet light through at shorter wavelengths than does the other lens. So one of these lenses, the one marked by the yellow curve, actually allows more ultraviolet light through the lens. So think about an instance in which you as an optometrist would want to prescribe the lens material with the blue curve rather than the lens material with the yellow curve to any particular patient. Here's another concept checked. Contrast enhancement during night driving, shooting, and hunting can be enhanced by a certain color of filter. These yellow filters, as modeled by these two actors here, actually absorb which wavelengths? All right, so let's just take a look at their filters again. The yellow lens is yellow because the yellow wavelengths are getting through. So now think about what wavelengths are not getting through, and those are the wavelengths that are absorbed. Let's think about just a yellow lens in general. There is some clinical application to the concept that we introduced on the previous slide. So on the photograph over here on the left, as people age, their natural lens or their crystalline lens starts to become yellowish, and so that lens, that natural lens in our eye, actually will filter out some of the blue wavelengths of light so that blue light does not get to the retina. If you remember from class, the photon energy is higher for blue light than it is for red light, so blue light and ultraviolet light is more photooxidative, more potentially damaging to the retina. So by developing this yellowed lens as we get older, it does in fact actually protect our retinas from some of that damaging light. Now, if this lens inside of our eye becomes too opaque, it will also hamper or hinder our vision, and so eventually this cataract will need to be removed and an artificial lens put in place so that we don't have to wear super thick eyeglasses. So over on the right, we've actually got the transmission spectrum of several different intraocular lenses, and we're also with the black curves showing you the transmission spectrum of natural or crystalline human lenses. Again, on the x-axis, we've got wavelength. On the y-axis, we have the percent of the light of the different wavelengths that the lens is allowing through. So none of our lenses, even that of a 30-year-old, which is the one here, none of these lenses actually allow much light through that is shorter than about 400. But if you put the intraocular lens in that has the transmission characteristics denoted by the red curve, that lens is going to allow more ultraviolet light through compared to the other two intraocular lenses. So in many older individuals, that would be perfectly fine because their retinas are nice and healthy, but there are other individuals who have some pathologies in their retina, and we would want to protect their retina from photooxidative damage, and so we can suggest to the surgeon that they put in an intraocular lens for that patient that also blocks more of the ultraviolet light. This slide introduces this concept called a neutral density filter. Let's take a look at the graph on the left first. We have wavelength on the x-axis, again highlighting the visible spectrum, and on the y-axis we have percent transmission. Now in the lens over here, on the y-axis, rather than plotting actual percentage points, there is a unit that we can use. Well, it's not really a unit, it's a concept that we use called optical density. So over here, the optical density value can be calculated if we know the transmission of that density filter in percent. So you take 1 divided by the transmission of the filter expressed in decimal form. So if it's a 50% transmission filter, it would be 1 divided by 0.5. And then after you calculate that value, you take the log base 10 of that value, and the number that you get is the optical density of that filter. So there's an advantage to calculating the optical densities of these neutral density filters rather than using their transmission values, because optical densities add. So if we need, for example, a 7.0 optical density filter, but all we have is a 3.0 and a 4.0, we can place those two filters one right on top of the other, and the combination will have the same transmission characteristics as a 7.0 optical density filter. One reason neutral density filters are used is because they offer or provide a minimum distortion of colors. So if you need sun wear but you don't want your color perception distorted when you're outside driving or what have you, then you would want to prescribe a gray filter for their sun wear as opposed to brown or green or what have you. I'm just showing you down here that we sometimes have filters that can be connected to cameras to attenuate the light before it reaches the camera film or the digital receiver of the light, and we use them, neutral density filters, for many reasons in optometry, and we will be going over these with you over the course of the next year or so. Let's talk about what happens when we combine multiple colored filters together. Over on the left, we have a diagram which represents how white light is affected if that white light passes through different colors of filters. So we have a single filter being shown top, middle, and bottom. So the artist has represented this white light as a combination of red, green, and blue light, and for a magenta filter, the magenta will actually filter out the green light so that the red and the blue light pass through. So when red light and blue light are combined, the color looks magenta. And the graph over here shows the characteristics, the transmission characteristics of that magenta filter. So this would be called a band stop filter because it allows a section of wavelengths through on either side of this middle section here where the wavelengths are blocked. With respect to a yellow filter, the filter looks yellow because it allows red and green light to pass through, but it blocks the blue. So when red light and green light combine, the light looks yellow to us. So this yellow filter has the transmission curve shown over here. A cyan filter looks cyan to us because it blocks red light and allows the green and blue light through. So when green light and blue light get mixed together, it looks cyan in color to us. And over here to the right, we see the transmission curve of the cyan filter. Now, if we take two of these filters and lay one on top of the other, we can see what happens to the light coming out of the filter combination. So if we take a magenta filter and we combine it with a yellow filter, we have the red and blue light coming out of the magenta filter and entering the yellow filter, but now the yellow filter will block the blue light so that only red light comes out of the filter. So if you were to have a magenta filter and a yellow filter and hold them together, they should look red to you, or the combination should look red to you when you hold it in your hand. Similarly, if you have a white light entering a yellow filter, we've got red and green light coming out. And if now that red and green light encounters the cyan filter, the red will get blocked and green light comes out. And so when you hold that filter combination in your hand, it should look green to you. And then you can kind of walk through the blue filter appearance from the combination of the cyan and magenta filters shown on the bottom. What would happen to the final transmission of the light if you actually take the magenta, yellow, and cyan filters and stack all of them together?